me. So some applications of double integrals, one application which is nice is you can use it to find the area between two curves, which is not that great because you already know from Calculus 1 how to use a single integral to find area between curves. So it's almost like adds a layer of complexity. Like, why would I want to do that? Because it preps you to get ready for the more difficult and challenging applications. So you have to know how to do that. So it turns out that the order of integration is also important. So if you have dy dx, that's known as the vertically simple choice for integration. That's my personal favorite because that means you can leave all the functions as functions of x. The other order of integration is less of a favorite, dx dy, and that's when your region is known as horizontally simple. So your little man, if you're going to put your little man in there, he has to be lying sideways where his head is to the right and his feet are to the left. Vertically simple, if you're going to put your little cross section, you could just use a rectangle, but I like the little man idea. He has to be sitting vertically in your region. And so the top of his head is the taller, feet shorter, so on. So we did some examples of finding area between curves. And we also looked at some examples where you had to switch the order of integration. And I think the last example I left you with is we had to do a little bit of work in order to find the area of a region because it wasn't the kind of region where you could just treat it with a single integral because the limits change depending on if you were one area of the region or another. So this was a region we had to chop into two pieces in order to attack it, okay? And there's no other way around it. Like, don't come up to me after class, is there a shortcut way to do that? Where there's just a single integral? And the answer is no. If I knew it, I would teach it to you, okay? You get all my wisdom. I teach you all my tricks. The question is, do you want to hear it? Sometimes I wonder if my Calculus 2 people do. They don't listen to anything I say. I tell them in class, if you do it this way, I'm not going to give you any credit. And then what do? They do it that way. And then I take away their credit. And then the next quiz, they do it again. It's like, wow, okay. Let's talk about something you already know from Calculus 1. Good news, in Calculus 1, you talked about something called average value. And so what did they talk about? Let's do a quick, brief Calc 1 review, because then we're going to extend it to Calc 3. So do you remember this concept of average value? The average value for one variable over an interval AB is, and I don't know the notation, some books say F and then they do a subscript AV, that means F average. If you've taken statistics or you look at another calculus book, average, they usually put a bar over the top, and that means average, so average of F. And in Calc 1, it's really easy. Oops, I need some more room here. You're going to evaluate the integral going from A to B, and you're going to divide by the length of the interval. So the length of the interval is B minus A. I mean, if you look at what they're trying to do here is you're just trying to find the average height of, all the y coordinates on that interval. And so this length here between A and B, and want to talk about a lag here. I'm getting a big lag with my pen. This length is B minus A. And so if, for those of you that know how to take an average of tests, you add up all the scores and you divide by how many tests you took. This is very similar because you're basically adding up all of the y values. Why? Because an integral really is a sum. I mean, it's derived from a Riemann sum. So you're adding up all of the y values on the interval A to B, and you're dividing out by the number of tests. Well, in here it's the length of the interval. So it's got that average feel. Sum of all the tests divided by the number of data. So in 3D, the way it's going to look, if you've got a function of two variables, say z is equal to fxy, so we'll just do a kind of a cool capping surface like that. And you want to find the average height, the average z coordinates. Your f average here, however you denote it, is you're going to take a double integral. And now here's some of the notation, so don't freak out. This capping surface is hovering over a region R of integration. And so you'd have to figure out what the limits would be on the integral, but the generic way to do it is just to put a big R underneath your double integrals. And yes, I'm going to use that notation a lot for the rest of the semester, so please get used to it. So you're integrating over a region, not an interval. And you're going to integrate the function. And now normally here, you're going to put the x dy, or you're going to put dy dx, one or the other, depending on your choice of integration, whichever is easiest. But this is an area. It's delta x, delta y. So the generic way to denote this is dA, the change of area there. Okay, and you're going to, after you figure out what the result of that double integral is, you're going to divide by the area of the region that you're integrating over, which is this region down here in the xy plane, which the capping surface is hovering over. Okay, so that's the definition of average value for us here in Calc 3. So let's do a problem. We'll do an easy one. So we want to find the average value of this function, fxy equals 4 minus x minus y. By the way, this is a plane equation. Can you tell? Because if you replace fxy with z, it's a plane equation. And so that capping surface is essentially a plane, and it's hovering over a region in the xy plane. So if I had to graph that plane, you guys all know how to graph planes. If you added x and y to both sides and just sort of rewrote it, it looks like that. And so I hope you can see that a portion of the plane just looks like that. But we want the average value of z where this is hovering over a region here in the xy plane. So in the xy plane, the region of integration is going to have x going from 0 to 2 and y going from 0 to 3. So it's just a rectangular equation, okay? So our F average is going to be 1 over the area of the region multiplied with the double integral over that region of the function 4 minus x minus y. Now the dA, I'm going to choose my favorite order of integration. That's the vertically simple dy dx. Now I have to iterate the integral. So this is the part where it gets a little tricky, but because they gave you the region in set notation already, they gave you the limits. They handed it to you on a silver platter. Yeah? So does anybody see what the limits would be for the x? So I'll have to figure out what I put on the outermost integral symbol. What would those limits be?
0 to 2.
Yeah, because they told you right there in the set notation for that region. And then the limits for y?
Yeah, that's going to be 0 to 3.
Mm-hmm. And so what is the area of this region? Well, that's easy because it's a rectangle. So the area of the region is just going to be, length times width, or 2 times 3, which is a constant. So that's good. Otherwise, you'd have to go do another integral to find out the area of the region if the region were really weird. But this is just a constant. So we have 1/6, and now let's do the integration. So when we integrate the innermost integral first, and it's important that you get that this is just partial differentiation backwards, you're going to integrate with respect to y, which means you're going to treat x as if it were a pure number, like 7, and you're going to integrate with respect to y. So the antiderivative of 4 is 4y when you're integrating with respect to y. And then minus, the next term is xy, because x is a constant, minus y squared over 2. And so you're going to evaluate that expression between the limits of 0 and 3. And of course, when you're all done, you still have to worry about the other integral that you need to keep doing. So here, I'm just going to do this really quick. Just use my fundamental theorem, and I'm plugging this 3 everywhere I see the letter y, not x's, because we just integrated with respect to y. So leave x alone. He just stays x. And then when I plug in zeros everywhere, I'm just going to get a big old 0. So I'll just kind of represent that. And then dx. Do you always get a 0? No, but this is a polynomial, so you will. So here, I'm now going to get what? I'm still going to have a 1/6 out here. And I'm going to have a 12 minus 3x minus 9/2. I'm going to collect like terms. What is 12 minus 9/2? I think it's 24/2 minus 9/2, which is 15/2. So I'm just going to collect those constants before I integrate with respect to x. So that's, you don't have to, but it's up to you. You'll have to do it at the end anyways. Okay, so this is an easy calculus 1 problem at this point in time. So I'm going to have 1/6 times 15 halves x minus 3 halves x squared, and I'll evaluate going from 0 to 2. And so then I'm just going to say, etc. You know how to plug all this in. I get an average value of 3 halves for the function, and I'm done. After I multiply by 1/6, and we're done. So finding average value is going to be on this week's quiz. I think I put 2 problems that have to do with average value. So know how to do it. Okay, it's on the homework. You do your homework, you'll be fine. You'll go, oh, I saw that problem already. Great. So you'll be fine. Okay, so I encourage you to do your My Math Lab homework. And if you ever get stuck on My Math Lab homework, some of the students who do come to my office hours, they'll even tell you, I'll pull up My Math Lab and we'll go work the problem. Whichever problem you want. You just tell me, oh, it's in, the homework on 15-6. Let's do, problem 18. Okay, let's go do it. Okay, any questions on average value?
How did you find the area of the region for that?
Well, this region was super easy because the region is just a rectangle. So you know how to find the area of a rectangle?
Yeah.
Length times width?
Mm.
So 2 times 3 is 6?
Oh, okay. All right.
Yeah?
Yeah.
Now, if that region were real curvy, let me just tell you, it'd be more of a nightmare. Why? Well, let's say the region that you were integrating that 4 minus x minus y over was something a little bit more curvy. Like, let's say it was this region right here that I made you guys do. Remember, I had you guys go in pairs, buddy up, and do this region. This little sliver here. Does anybody remember that?
Yes.
So this is your R here. So you couldn't go, well, the region is length times width. That ain't no rectangle. You would actually have to figure out what the region's area is. And it might take some work. Like, looky here. Oh my goodness. We had to set up a double integral and we ended up with the area of that region being what, 5/12? So if you were doing this problem that we were just doing and your region wasn't a cute little rectangle where the limit, you notice when you do have a rectangular region though, all your limits are pure numbers. Remember we talked about that last time? See these limits here?
Right.
See, they're all pure numbers. That's how you know, boom, your region is going to be a rectangle. It's when you even have one variable in the mix, it ain't going to be a rectangle, okay? So if that were the region we were integrating over, when we did 1 over area of R, we would have had to go 1 divided by 5/12. Ooh, and that would have taken some more work. All right, now we're going to do improper integrals. And I love this. This is like love. Love. Come on, don't give up on me now. Why do I love improper integrals? Well, it's the same reason I love it when I teach it to Calc 2, which they just learned it last week. Because it combines limits with integration, all in one lovely, tidy package. So you got to know a lot of material just to do an iterated improper integral. So what makes it improper? Well, there's a couple things, but we'll stick to one type of improper in this course. What if one of your limits is infinity, or maybe negative infinity could be one of your limits? That makes it improper. And these are fun. So I know the book makes you replace the infinity with a letter like A and then take the limit as A goes to infinity. I don't do any of that. So when you hit the show an example button and it says go do that first, don't. Just do it my way. I'm giving you the shortcut way. Okay, I'm not going to require that you write lim and replace it with a letter and take the limit as it goes to infinity. Now, for those of you who don't listen to me and you're like, well, I'm just going to do it my way, fine. But I'm giving you what's an okay shortcut. And like half my Calculus 2 students just don't listen to me. I did tons of examples. Don't bother. Do it the quick and shortcut way, and you'll be fine. And they just ignored me. And on their midterm they took Monday, I won't mark you wrong, but you don't have to. So let's do a couple of improper integrals because you're definitely going to have one of those on the quiz. And they're easy if you know how to integrate and you know how to take your limits and you know all your limit facts. And I already went over all your limit facts. So keep that handy when you're taking your quiz. Oh, there's one other thing I wanted to mention. When I teach face-to-face, which I just found out from my union rep that might not even be next fall. Don't get me started, okay. When I teach face-to-face, I allow my students, when they're taking a midterm, to have a cheat sheet of formulas and theorems and definitions, front and back, okay? And they can bring that to the exam And when we're sitting face to face, they have that, they don't get all their notes and books like you guys get because you're now online, but they get their cheat sheet. So for those of you who might want to like spruce up your scores for the rest of the semester, have you considered making a cheat sheet for an exam? It's just a thought. Like, you know, maybe you want to have all the formulas handy on one piece of paper so you don't have to go thumbing through your course reader or whatever else you're looking through. So it's just something else that could give you a little bit more speed, give you an advantage because I'm testing fluency. And if you're spending too much time looking through notes, you don't have it. You don't know it. Yeah, I do. No, you don't. Okay. There's no argument here. You don't know it. Okay. If you're having to go think about it and look up stuff, it's not in the just right there at your fingertips, you know, at the tip of your tongue, or you can't do it in your sleep. So that's how I want you to get. Know it. And that involves some memory, so do it. So let's take a look here. What are we going to do? Well, this is going to test your integration. And one of the reasons why I spend a lot of time on integrating in the vector valued function module when we integrate vector valued functions is so you're ready for this chapter. So you'll thank me later if you were paying attention. How do you integrate this beast with respect to y? Any ideas besides George? And remember, the x squared is just a constant, so you can treat that as like a 10 or something. So more importantly, you're really looking at how do you integrate 1 over 1 plus y squared with respect to y. So I'll give you some choices. Do you use the log rule, the power rule, the arctan rule? Do you have to do partial fraction decomp? Do I have to do trig sub? What do I need?
Is it
arctano?
Yes, it's the arctan rule. Very good. This is an arctan type of integration problem. Does everybody see that?
Yes.
Now, when you're doing an arctan rule in my class, I want to see the U and the DU and the A. Otherwise, I won't give you full credit. In fact, you might not even receive credit because there's a lot of apps out there that some students are cheating off of. And those apps show you all the steps, but they neglect to show you the U, DU. And that's kind of how I know there's cheating involved. So I even told my Calc 2 students this, and what did they do? A lot of them didn't tell me the U, DU, and A on their midterm, and I just took away all their points. It's very easy. The U is just y. The derivative of y is 1 dy, and a for us is 1, because this is, for those of you who didn't have a good Calculus 2 experience, this is your arctan rule. Okay, I've done this before, but this is, you know, what I want to see here. Now, of course, plus c, but what I want to tell you, a little secret, every time you do a double or triple integral in this class, you will never, ever, ever, ever have a plus c. If I catch you doing one, I'm going to take away points. Well, why not? That was a big deal in Calculus 1 and Calculus 2. I know. But in this class, all iterated integrals have a final answer that's a pure number because they're all definite integrals. Okay? No plus c's. I don't want to see it. Okay, so you're going to do your arctan rule. So what am I saying? So you still have the x squared there, and then this is just going to be arctan y, and you're going to evaluate that guy between 0 and infinity, but you still have another integral to do, so I'm going to continue to write it down. Now, here's where I need your limit facts. When I plug in the upper limit first, I get arctan infinity, and then plug in the lower limit, arctan 0. You have to remember what arctan infinity is. Does anybody remember what that is?
Over to
Pi halves.
Pi halves, very good. And how about arctan of 0?
0.
It's 0. So this is just, this whole difference is just going to be pi halves. Oh, nice. It's just a constant. So I can pull it out of the integral. Lovely. And then everybody in this room better know how to integrate x squared. Otherwise, we're in deep trouble. And then you'll evaluate that. And I get a final answer after reducing the lowest terms of 9 pi halves. So we can say that the improper integral converges. Remember that? Converging and diverging. So if you get a finite value, it definitely converges. Okay? Questions on that one? Improper integrals?
X squared. Oh yeah, that was just a constant from the first integral, right?
That's right. Yeah.
Okay.
Yeah, when you integrate with respect to y, you treat x or x squared or anything that has x's in it only just as a constant. It's like a constant multiple.
Okay, thank you.
You're welcome. Okay, now we're going to do something a little bit more tricky. Check out that baby. Woo! I love this one. when I teach differential equations, I actually do something similar to this, where I convert to polar, and this is how I teach when we do the gamma function with Laplace transforms. What the heck am I talking about? Yay, take differential equations. Hopefully they cover it because it's kind of fun. But I want to give you a theorem first, a little fact that you can't use it all the time, but if you can, it's awesome. So let me give you a fact that'll make this problem easier to do. If you're integrating some double integral or a triple, but you're like, oh, and the integrand is such that you can separate all the x stuff and separate all the y stuff where it looks like a product. You can't do this if it's a sum. Like if it's like x plus y, oh, I can do it. No, you can't. It would have to look like x times y, where you could actually rewrite it as a product. Then here is what you're allowed to do. Let's say this is dy dx. You can rewrite it as two separate integrals. Now, by the way, don't be doing this all the time. I catch you doing this like, well, you said I could do it. Oh, God. You know, the way students twist my words around. Unbelievable. So you integrate the f of x with respect to x, whatever, you know, his limits are, times, this has to be product, whatever the limits were for the g guy, dy. So this is legal, but if and only if you can actually write the integrand as a product of two separate functions, one that's a function of a single variable and the other one that's a function of the other single variable, okay? Otherwise, don't even think about it. So I claim this one we can. Well, what do you mean? Well, I'm going to use exponent laws, so I still have the x times the y, big whoop. But after distributing the negative, it looks like e to the negative 2x minus y squared, and then using an exponent law, this is actually equivalent to e to the negative 2x multiplied with e to the negative y squared. Now what? Well, if I regroup everything, where I put the x's next to each other like this, and that's the function of x, times the rest of these products here. So now this is looking like f of x times g of y. Beautiful. So what does that mean? I can just integrate the separate integrals. So this integral here becomes the integral going from 0 to infinity of x to the times e to the negative 2x dx. And then we're going to get whatever that result is, fun. And then times the integral going from 0 to infinity of y e to the negative y squared dy. Okay, does everybody see the setup here that you can do that for this problem, which is kind of cool?
Cool.
Yes.
I mean, you should be saying cool beans right now. It's awesome. So I'm going to probably run out of room here, so give myself some more room. So now what? So now I claim that these are, one of the integrals is a calc. Jeez, the game's great. One of the integrals is an IBP problem. Can you see that this one right here is IBP, integration by parts? And the other one is not IBP. This one is just the exponential rule. So we'll do each of these in turn, okay? And this is good review because, yes, it's still important for you to know how to do IBP. We're in an integration chapter right now, so I'm going to ask you to integrate all kinds of things. Good news, though. I promise I will never, ever, ever ask you to do trig sub. You're welcome.
Thank you.
You're welcome. I will ask you to do IBP and power reduction formula. You'll see. Okay, so if I do the IBP problem, what do I know? Well, when you do an IBP, if you not write the following down, you won't receive credit. I want to see the U. I want you to identify the dV. Then go get the du, and then go get the v. And actually tell me, if you skip this very important core step, that means, I don't know where you got it. Like, don't do this in your head. I'm not going to buy it. I don't even do this in my head. That means you were looking at some app. So you know the drill. It's u times v minus the integral of v times du. That's the formula. So what are we going to get for r's? After ru is going to be x. The dv will be the rest of the integrand, e to the negative 2x dx. And so du is just 1 dx. And v, the integral of e to the negative 2x. Be careful you don't take the derivative. That's a common student mistake. I see it a lot in Calc 2, but I better not see it here. Okay, and so then you're going to go, okay, u times v. So you're going to go x times negative a half e to the negative 2x minus the integral of v du. Okay, what do we got? What do we got? Goodness. Now, I'm not evaluating at the limits yet. I'm going to hold off until I get the full antiderivative. This here, even though this is e to the negative 2x, normally I let you leave your exponentials with negative exponents. I don't care. But this time, I'm going to rewrite it because I'm going to evaluate it in a moment at the limits. So you'll see it'd be easier for me. This antiderivative, I'm going to pull the negative half out. And when I integrate this e to the negative 2x, which we just did, that's negative a half e to the negative 2x. Okay, fine. Now I'm going to take this big old antiderivative and evaluate between the limits of 0 and infinity. Okay, and then you're going to use your limit facts. So when you plug in infinity here, you're going to have negative infinity over 2e to the infinity. And then this is a minus minus, that's a plus. But then I have a negative a half here. Oh, never mind. I guess I'm going to have a minus again. Let me just double check. Sometimes I make mistakes here. Oh, I think we're okay. Wow, what am I doing here? Oh, I'm doing these all together. Nice. Interesting. Okay, so we have when we have minus a half e to the negative infinity, and then now plug in your 0. Okay, so minus, well, this first term is just going to be 0. Then we have minus a half e to the 0. Okay, so what are we going to get here? What does e to the negative infinity go to? Does anybody remember their limit facts?
0.
Good, 0. How about infinity over e to the infinity?
It's by growth rates. 0.
Yeah, you're gonna e to the infinity is infinity. You could use L'Hopital's right now. That would be legit because that's an expression of a single variable. But if you remember growth rates, if you have a polynomial and it's divided by an exponential, do you remember that exponentials go to infinity faster? So if the one that's going to infinity faster is in the denominator, this whole thing goes to 0. Great. So this whole thing is 0, and then you distribute your negative, and I get plus 1/2. So save that for later, because now you're going to go do the other integral. Well, what other integral? The one that you don't need IBP. Good news. That's this guy here. So I'm going to use the exponential rule, which just says the integral of e to the u du is just e to the u. And when I use my u substitution with my exponential rule, I get u as negative y squared, du is negative 2y dy. I already have a y and a dy in the integrand. Good news. I just wish I had a negative 2. So you put one in, provided you divide one out. So now the intermediate step looks like this, which I'd like for you to do on your exams, please, so I can see that you know what you're doing. And then I back substitute for u, which was negative y squared. And then this guy's limits were also 0 to infinity. So if I plug in my upper limit, I have negative a half e to the negative infinity minus 0. So I'm going to plug in 0 here, negative a half e to the 0. But this goes to 0, and the minus minus is a plus, right? I'm just looking here to see if I did something wrong. Oh, yeah, I know what. I didn't. So this is also looking like it's going to be a half. And so what's your final answer? Anybody have an idea?
Is it 1/4?
Yeah, you're going to multiply these results because we were multiplying those two integrals together. So you're going to have a half times a half is 1/4. And so your final answer is, hey, the improper integral converges, and it converges to 1/4. Cool. And I'm done talking about improper integrals. Okay, new topic for example 10. Questions?
I'm fine.
Okay, so this last example before we go into the more meat and potatoes of double integrals. We're not done with double integrals, not even close. Okay, like Friday, I'm going to start polar coordinate system. So you'll get to see something really fun when we get into polar. So is that important? Yeah, you learned polar in Calc 2, remember? It's coming back. So the cool problem I want you to see here in example 10, I'm not sure Briggs even has this where they show it to you. They just go, yeah, you should know it. And I hate it when books do that, where they don't talk about it in the text, and then all of a sudden you get one of these wacky homework problems like, ooh. So I want you to see this flavor, although it should be easy to grasp. So I just want to say that, let's say that you had a problem like this, e to the x squared dx. Do you guys get that this is not integrable?
Right, right.
Well, I can use exponential rule. No, you can't, because if you try, you're going to go, okay, well, u is x squared, but du is 2x dx. And I'm like, ugh. I can always put in a constant multiple of 2, but if I'm missing a variable, you're not allowed to put a variable in. So don't even think about doing that. Okay, e to the x squared is a classic not integrable integral. And in fact, that's one of the cool things for those of you who had me for Calc 2. I don't know if you remember, but I took this guy in particular and we used the fact that e to the x was, you guys remember this?
What was that? The power series or is it Taylor? What was it called?
Do you remember this at all?
No.
Did you think this was going away? Don't worry, we're not going to do that here in this class. I'm just sort of bringing back some bad memories for you, just to see if you forgot everything you learned in Calc 2. So what we ended up doing is if e to the x is this, e to the x squared is everywhere you see an x, you replace it with?
Squared.
And then what? Now you integrate this. And this, because it's a polynomial, you can integrate it. That's the whole point. Okay? Power series. In case you missed the whole Calc 2, like what was the reason for living there because of the pandemic, one of the cool things that comes out of power series, which is this right here, that's a power series, is you can use it to help you integrate stuff that's not integrable because you just get a lovely polynomial if you're using that Taylor series. Yeah? Okay, so that has nothing to do with this problem. I just went off on a tangent. Fooled ya. Now what? Well, then how do we integrate this thing? All right, carefully. So you always do the innermost integral first. And you're like, oh man, okay, is that even integrable? Oh, yeah, tangent plane, I say. Tangent plane. Okay, how do I integrate e to the x divided by y squared with respect to x? I claim the exponential rule will work. So here's what you're going to do. You're going to go, really? The exponential rule? Yeah, e to the integral of e to the u du is e to the u. I swear to God, this is true. Well, prove it. Well, I'm gonna. So using u sub, I'm going to say that u is the little exponent there, x over y squared. And then du, now remember, when you find the du, you have to be careful and remember what is your variable of integration at that moment. At that moment right now, we're integrating with respect to x. So y's look like constants. So when you're doing your du, you're differentiating with respect to x. So the derivative of x over y squared with respect to x is 1 over y squared dx. Now here's the thing. This is not appearing in the integral at this time, and I need it to. And well, am I allowed to put variables in? You just got done telling me over here in Calc 1, you're not allowed to put in variables if you're missing one. Yeah, but if you need a variable that's not the variable of integration, because it means that variable is really a constant at that time, you can. So what you're going to do for this integral here, and let me just keep going here. I'm still going to have the outer integral, so let me just copy it down. So the inner integral now, if I put in, I'll change colors here. You still have this e to the x over y squared dx happening, but I need a 1 over y squared to be the du portion, which means I have to multiply the front of that integral by the reciprocal in order to make it legit, okay? So this is looking like a constant right now, and that's the cool part of this problem. So now this, and I still have a dx out here to match this outermost integral. This has the look of e to the u du, and so the result will be e to the u, which for us is e to the x over y squared. And you still have this y squared sitting out here. You'll use it up later. And so you're going to evaluate this guy between the limits of, I just turn the page so I forget, 0 to y squared, like so. Okay, so this is supposed to be dy. Sorry, this should be dx. I don't know what I was thinking. My bad. Okay, we're in the middle of evaluating with respect to x. So now when I substitute the upper limit, I'm going to replace the x with it. Okay, so I'll do this kind of slow here. So I'm going to go, oops, I'm done integrating. What am I doing here? You're going to go e to the y squared over y squared minus, and then when you substitute in the 0, e to the 0 over y squared, but that's just 0, and e to the 0 is 1. This reduces to a 1, so this is just e minus 1. And that's just some weird number. Just some constant. I'm going to just pull it out in front of the integral because it's just kind of weird looking. And then go ahead and integrate y squared with respect to y, which is easy because now it's just a Calc 1 problem. And so you're just going to go, okay, y cubed over 3. And the limits on that outermost integral were from 1 to 2. And so then if you plug in your 2 first and so on, you'll get this weird number. And my final answer is e minus 1 times 7/3. That's the exact answer. Okay, I know, weird. Sometimes you get weird answers. Okay, so I just wanted to show you that it is legal if your du portion needs a variable, but the variable isn't your constant, or it's constant with respect to your variable of integration. Cool. I think it's cool. So that's something that you can think about if you're integrating. Okay, questions?
No, I don't have any questions. Thank you.
Okay, so just to recap, you can put in a variable if it's not really a variable with respect to the integration, okay? So when it says provided that, you're provided that it's a constant with respect to the variable of integration. That's when it's legal with respect to constant of integration, okay? So back to reality. All right, so we got about 20 minutes left. And look, I know it's hard to Zoom all the time. Do you think I like Zooming anything? It's harsh. You know, it's easy just to tune out and pass out and not pay attention. I get it. But you have to kind of do your part and drink a lot of coffee and do your best, you know? You know, the old saying, act as if, you know, act as if you care. I don't know, but, you know, I know you guys are here because you want to better yourselves. You're trying to get your education. You want to improve your life. And that's why you're here, right? So sometimes it takes digging in, you know, and stretching your uncomfortability out there and getting some feedback that kind of makes you unhappy or depressed. And then saying, okay, well, one test score does not make me as a person. Okay. It just happened. Move on. Okay. I've had that kind of stuff happen to me all the time. I remember I was in grad school, one midterm, one final. And I got a D on the midterm. So I cried the whole semester long till the final hit. Okay. I ended up with an A- in the class, but that was because I really studied my butt off the second half. While I was crying, you know, of course, tears, lots of tears. You know, but I give you plenty of opportunity to dig yourself out of the hole. You know, I give you lots of quizzes along the way. So I give you regular feedback to let you know if you're getting it or not. That class didn't have any feedback. I didn't know what was going to be on those exams. So there's my meme. And let's do double integrals. Okay, with volume. So what about it? So there's a fun application of double integrals than finding area between two curves. I think it's more fun. It's very exciting. Using it to find the volume of a solid. Not solids of revolution, okay? Forget that. We're not doing that. We're not going there. Thank God, all right? This is way more fun. Like, you're going to love it. And if you're not having fun with this material, I got to tell you, you're not doing it right because it's really exciting. You're going to like it. So let me do the hand-waving penumbra of a proof to get us to the Riemann sum, take a limit, so we can get our volume, just like you saw in Calc 1, where they got a Riemann sum of all the rectangles, took a limit as, you know, more and more rectangles and so on. So we're going to do something similar here in Calc 3, but we're not going to use rectangles. We're going to use rectangular prisms. Okay, so here's the derivation. You got your function. f. And for now, consider it to be a positive function. So consider all the altitudes. The surface lies above the xy plane, kind of like this picture here. Here's your surface of some solid. There's your capping surface. And what are you trying to do? No, Nicholas, we're not spinning 2D objects into 3D ones. Yeah, forget that. That sucks, okay? If you want to keep doing that, knock yourself out. We're not doing that, okay? This is much more fun, much easier. Okay, so play along here. You're going to like it. So you got your capping surface of your solid. And I have no idea what you're talking about, Nicholas G. Okay, yeah, I think David's got on the right track. Go major in pottery. All right, so you've got your solid. Now down here at the base of the solid, so here's the base of your solid. You're going to partition the base into a bunch of little teeny bitty rectangles, okay, lying within this base, which basically is your region R that you're integrating on, okay? That's your region R that we were talking about when we were getting average value, okay? Now, all these little itty bitty rectangles are making what's called an inner partition, and they name the partition with this big delta. And then the norm of the partition, which looks like you're taking a magnitude, that's just the length of the longest little itty bitty diagonal of a rectangle inside the partition. Fine, okay, whatever. Choose an arbitrary little rectangle, and then choose an arbitrary point inside that rectangle, and then form a prism whose height is f evaluated at that point, x sub I, y sub I. So if you look at this picture right here, you see this rectangular prism. So what we're going to do is, I don't know how to find the volume of that solid because I don't know the formula for finding the volume of a solid that's got like a curvy top. I can find the volume of a box, but nothing like that. So the idea is, let's use something I do know how to find the volume of. I do know how to find the volume of a little rectangular prism, you know, just width times length times height. So that's exactly what we're going to do. Where delta A sub I is, if you take one of these ith rectangles down here, let's say one of these ith, you look at it like this, you know, you're going to have delta x and delta y. So the area is going to be delta x times delta I, width times length, and they're going to call that delta A sub I. Okay, they're just using this kind of notation with I subscript notation. And if you're a math major, you better love this stuff. This is all you're going to do, okay? And if you're like, oh, I didn't know math majors did all that, welcome to engineering degree. Delta A sub I. Now the volume of this prism is going to be the base area times the height. So the volume is going to be the area of the base, which we already got, you know, it's length times width, times its height. But the height is the z altitude. It's f evaluated at x sub I, y sub I. So there's your height, there's your area of the base, and then you take a Riemann sum because you're going to form a whole bunch of little prisms like this and add them all up. And let's say there's n of them. Now, this looks like a pretty good approximation of the actual volume of our solid. And so you can imagine what's going to happen. Just firm up the partition and make the prisms even skinnier and skinnier, and take a limit as the norm of your partition goes to 0. And so this is the limit of the Riemann sum that all good math majors learn. And what happens is we're going to get to the definition of a double integral right here. So when you take the limit of your Riemann sum, it turns into, voila, your double integral, where the delta A sub I turns into dA, and you are integrating over a region R. And of course, you hope the limit exists, because that means the function's integrable. Because if it doesn't exist, the function's not integrable. And we already talked about there are functions out there that are not integrable. Okay? Now, sufficient conditions for your double integral to exist, that you want R to be kind of special. R can be written in a very special way as a union of a finite number of non-overlapping regions. Is a union of a finite number of non-overlapping regions. It has to be kind of pretty, otherwise it's not going to work. Now, we're not going to run into any times where our regions aren't going to be this, so don't worry about it, okay? I'm just trying to give you the official definition. Okay, let's keep moving on. So what could you use this double integral for? Well, one of many applications. Don't come up to me after class and think you know everything after that, okay? This is one of like a whole bunch of things we're going to do with double integrals for the rest of the semester, okay? It's a fun one though. You already know one. One of them is finding area between two curves. Here's your second application, people. Application number 2, use a double integral to find volume of a solid. So if f is integrable, and that's your capping surface, and he's positive, because you want to get, positive volumes, and he's basically hovering over your region R, and this is the base of your solid. So we're not going to be revolving anything around axes. Don't get into that volumes of solids of revolution. That's not what we're doing here. Then the volume of the solid region is just the double integral that lies above your region. And the way you denote that is you put a big R underneath the two integrals. And dA is going to be one of two things. So this will be dy dx or dx dy, depending on what the base of your solid looks like. So you're going to have to choose. You want to be able to integrate, so you want to choose the correct choice. The order of integration matters. I think you remember last lecture last week where we had to switch the order of integration, otherwise it wasn't integrable. But after we switched it, it was. Okay, so how do you iterate the double integral? Because you're not going to just have a generic double integral over a region. You actually have to do the hard work and put the limits on there. And Fubini's theorem helps you iterate the double integral. So it basically just says, hey, if you've got a region that's vertically simple, where x is going from a pure number to a pure number, but y might be going from a variable to a variable, then your volume, your double integral, if you're using it for volume, you simply iterate it by putting the little limits up there, and then you can integrate with the order of integration being dy dx. This is my personal favorite, and it probably is going to be yours also, because you don't have to think in functions of y. On the other hand, if your region is defined a little differently, where y is going from a pure number to a pure number and x is variable, and you need those functions to be continuous, then you're going to iterate in the following way. So you're going to have y go from pure number to pure number, and then you still will integrate, and then your order of integration will be the horizontally simple choice. Okay, so now let's go get it. Let's go get a volume. All right, so this is an easy problem, and it's easy because we're just asking you to find the volume of a capping surface where the capping surface is a plane. Fine. So that's like the top of your solid. I do want to say that you do need to know this vocabulary. What do I mean by the solid is bounded by this plane and also the 3 coordinate planes? So if I were going to draw a picture of this, and you guys know how to sketch planes in space, I hope, you can start by finding the x, y, and z intercepts. And so here it looks like the x-intercept is going to be, 2? The y-intercept looks like it's going to be, a 1? And the z-intercept is also going to be a 2. So it's going to have this as the top, and then the 3 coordinate planes are going to just be the other 3 sides of this solid. So this solid kind of looks like a wedge. It's a wedge. Cool. Go find the volume of that wedge. Okay. Great. How do you do it? Carefully. So the first thing you're going to do, even if they don't ask you, is sketch the base of the solid in the XY plane. I may not ask you to do this either, but if you don't and you think, oh, I'm just going to skip this step because I do all this crap in my head, good luck. Good luck is all I can say. I'm teaching you the good practices, and good practices is sketch your base of your solid even if they don't ask you to. Well, how do I know what the base of the solid looks like? Well, look, it's right down there. There's your base of your solid. And you can see that this capping surface, because of this plane is kind of tilted, has a trace where it cuts right through the XY plane. So another way to deal with this, since z equals 0 in the XY plane, if you substitute z equals 0 into your plane equation, it looks like that. And that's kind of cool because when you solve for y and you draw what's going on here in the XY plane, this line right here has the equation 2 minus x over 2. And here's a sketch of the base of your solid. And the reason why you want to sketch your base of your solid, the motivation is it's going to help you iterate your double integral or put the limits on correctly. That's why you want to do it. Don't leave it to, I'll do it in my head. That's dangerous, dangerous, dangerous. So your volume is going to look like this. Boom, boom. You're going to have an integrand here, and then you're going to choose your order of integration. Okay, I'm going to choose my order of integration to be dy dx. You want to put your capping surface in the integrand. It's not going to be a 1. I already told you what the double integral represents if you use a 1 for an integrand. I'll open it up. Does anybody remember from last week what a double integral represents if the integrand is a 1?
Area.
Area between two curves. Remember that? That could be a good true-false question, right? Yeah. So what's my capping surface? I have to be really careful. I'm looking here and they gave me a plane equation. So do I just put the whole plane equation like this? Oh, x plus 2y plus z equals 2. Is that what you put in there?
I don't know.
No, that is not what you put in there. So what are you going to put in there? Anything?
Are you integrating the line? Or what are you?
Do we have to set equal 0?
Let's look back at you know what it says here in the volume solid definition. Look here. You don't put an equation in there. Come on. You're going to put a function. But they didn't give it to us using function notation. I taught you enough in the last chapter where you know this. You got this.
Solve for z?
Thank you. Solve for z. Very good. Very good. So you're going to need to solve for z because that is your fxy. So this one's pretty easy to solve for z. I'm just going to get z is equal to what? 2 minus x minus 2y. And that's my f of xy. So down here, don't put the equation. Come on, people. You don't integrate an equation. You know this. You're going to integrate a function. So you're like, okay, so I'm going to integrate this capping surface, which happens to have 2 minus x minus 2y. Now let's try to iterate the double integral. That means stick the limits on there. Don't guess. You'll go downhill. Like I give you some credit for the setup of your double integral. I'll give you some partial credit and then more partial credit for actually evaluating it. But if you set it up wrong, oh dear God, can't really give it to you. So don't blow this. So first up, if you choose the dy dx order of integration, dx is going to be the outermost integral. So good news, pure number limits. So what pure number to what pure number is going on this region of integration that we're integrating on, which is this little triangular?
0 to 2.
0 to 2 is correct. So that's going to be your limits for the outermost integral. Fantastic. Now what's y doing? Please do not say 0 to 1. I know the 1 is the highest that y can get. But if I stick a little man in here, you know, a little representative cross section, there's my little man, he's vertical. Do you see that, you know, it's arbitrary where I put him? If I slide him down here, he's shorter. If I put him over here, doesn't matter where I put him. Do you see that his head is going to be, you know, taller or shorter wherever I put him? So the upper limit is not going to be a constant for sure. It's going to be this line, which we already said was y equal 2 minus x over 2. So that's the upper limit for y. And the lower limit is where the little man's feet are resting. It looks like no matter where I slide him, he's always resting his feet on the x-axis, which has the equation y equals what?
0.
So if you have this somewhere on your paper, even if my math lab gives you 0 points, I will give you some points because congratulations, setting up the double integral to represent the volume is half the battle. Like if you get that part wrong, you know, and you got to think a little bit. It's not that easy to do this. This takes a little bit of skill, a little bit of knowledge. And now the integration part. So this is a little bit more rote. It's a little bit more of a pain in the butt. And so I'll start and then I'm going to show you that we're going to get into a little bit of a mess. It's going to be kind of painful. But If I integrate this with respect to y, I'll get 2y minus xy minus y squared. Fine. And you're going to evaluate that between the lower limit of 0 and an upper limit of 2 minus x over 2. And this is where it gets a little messy. Because, and I'll continue here, when you plug in 2 minus x over 2 for y, yeah. And then when you plug in 0, everything's going to go to 0 for this one, so you don't really have to bother. And then this is a Calc 1 problem. And it's not that hard, it's just tedious. So some things you can do to simplify this Calc 1 problem out a little bit to make you not have to work so hard. Of course, reduce if you can. You may want to, and this is up to you, split this up into 2 like this, and then reduce, and then distribute the x like that. So you'll get like minus x, and then you'll get plus x squared over 2. So these terms are very easy to integrate, okay? Over here, what about this beast? Well, it's 2 minus x squared over 4. You have 2 choices to deal with that last term. You can either expand it and multiply it out, FOIL it and get just all the little terms and all that, a big old polynomial or whatever. Or you can use u sub with the power rule. It's up to you how you want to treat that last term, where here you let u be 2 minus x, and then du is just negative 1 dx, and then you'd have u squared. So it's up to you. I'm just going to put et cetera, et cetera. It is a little bit of a pain in the butt, okay? Your final answer for this one is 2/3 units cubed, okay? So there's a volume. And by the way, your volumes had better be positive result. If you do a volume kind of problem, and for some reason you get a negative number, please redo the problem over because we don't have negative volumes, at least not in this class, okay? Now, there are going to be double integrals that we're going to evaluate that turn out to have negative answers, but those double integrals aren't ones that represent the volume of a solid. That's all, okay? So I'm done. See you later. I'll stay for 5 minutes. For those of you who want to come visit me for office hours, I encourage you to do so. Get some more solutions for your midterm. I'll be happy to do it, okay? Anything you want. That's what I'm here for, okay? See ya.